Okay, YouTube, in our last video, we looked at, I guess, the definition of a sequence and talked about how we could use the rule to find, any term in the sequence, or what we were generally refer to as the nth term of the sequence. In this video, what we're going to do is write the general pattern for the sequence and function notation. What I can tell you is, when I learned this the first time, I hated it. And I can tell you that I can give you some suggestions here, but really, the reason why I hate it is because creativity is not like one of my strong suits, but basically I kind of play around with the numbers here. Think about what do you see as a pattern here. So you're going to kind of fail and then try a different pattern and fail again, try a different pattern until you find something that works. And so what I'm going to do is I'm going to give you a list of suggestions over here, and you can take these for what they're worth. But when we talk about this, we'll list our suggestions, my suggestions as we go through. But we're going to write the rule here. So suggestion number one, I suppose we would write this. So we say write in domain and range form. So what we are going to do here is we're going to look at this pattern. And of course, I can generally see a pattern here. But what I want you to do is this. I want you to recognize that in terms of domain and range, we say our first term is 1, and our second term here, the weird thing is 3, and our third term is 5, and our fourth term is 7. If we were to look at this as a table of values, what you could see is that sometimes you'll see it written this way also. We could refer to our input as our n, and our output is, if I refer to the sequence as a sub n, I suppose, then this would be our output a sub n, what we get when we plug our term number into the function. So this domain and range form, what I want you to do is think about this just like a function. You think about this in terms of a sequence though. You just start with your domain at 1 and go on to, I guess, however long you need. So in terms of the rule, what we're going to do is we're going to say, well, what do we see is a general pattern here. And so what I see here is this plus 2, plus 2, plus 2. What you see here is a pattern that we recognize as linear. So what I'm going to do is I'm going to say, if there's a constant difference, if a constant, and we'll write a difference here, then linear. What I mean by a constant difference is, 3 minus 1 is 2, and 5 minus 3 is 2, and 7 minus 5 is 2. We'll refer to that later as a common difference, but we say a constant difference here between these things. So if we're going to write the rule, what I know is this. A sub n is how we'll write it here. And what you do is you recognize that, well, really what I'm doing is I'm taking my input and I must be doubling it. It's a linear situation. So my question is, does this work? Test your rule. Test your rule. And of course, I can tell you right now that this doesn't work. But if we test, if I say A1, I plug this in, I get 2 times 1, I get 2. My question is, how far off were we from what the output should have been, which is 1? And I noticed that 2 is just 1 bigger than what I should have gotten there. So what I'm going to tell you is that without now writing all this, that would have been scratch paper work anyways. We'll just say, what if I tried this, 2n minus 1? And so we say A1 here, this will be, 2 times 2 times 2 times 1 minus 1, apologies, 2 minus 1 is 1. So we get 1. If you try this for, say, A4 here, we can see 2 times 4 minus 1, of course, is 8 minus 1 is 7. So we do indeed get our fourth term. So that being said, you write domain or range form. And, if you have a constant difference, it's linear, and you test your rule. So let's take a look at these other patterns here and see what kind of patterns we can find. So this one here, we have 2 over 5. I'm going to write it this way. I like it better this way. 2 over 5, 2 over 25, 2 over 125. And remember what I said in the last video about rational things here, or at least not loosely defined as being rational, a ratio of two things. We're going to treat the top and the bottom as 2 different rules. So in terms of the rule here, we're going to write a rule. Actually, I'm going to call this one B sub n, this sequence B. And what I recognize is that I get a rule on top, and what I'm going to say is that rule is just 2. As a matter of fact, no matter what you plug in for n, you'll always get 2 on the top here, so we can recognize that that stays the same. So I suppose we would say look for constants, constant functions, constant things. They're not going to change, okay? And as far as the bottom, what I see here is this. I don't know if you see this also, but if you keep multiplying these by 5s, that's what's happening here. What I would recognize is then we could define this as 5 to the n. And if I say treat this as a separate rule, I might test this rule and say, what would be b sub 1? And I would say 5 to the 1, I get 5. But that is what we got on our first term in the denominator. So without testing all that, we can just say that this makes intuitive sense. So the next thing is this, if multiplying by a common factor, I'll refer to it as a factor for now, then it's exponential. And remember, exponential Just means this. We have a base b to the, I guess, nth power in this case, but we used to refer to it as x in function instances. So here's our rule for this term. So let's call this last one, let's call this c of n. And we say, well, what do I see going on here? Well, I'm going to look for, domain and range form here, I suppose. I didn't write that on that last one there. Shame on me. If we write this in domain and range form, our first term is 2, our second term is -5, our third term here is 10, and our fourth term here is -17. We say, what do we see going on here? What can I do to my initial n values here? These are n values here to give my cn values. And well, I guess I could look for a difference. There's no common difference here. This went down by 7. This is going up by 15. This one's going down by 27. I don't see anything there. We could look at second differences, but that's not anything I'm going to throw out there right now. So for right now, I say that didn't really work. How about, is there a number I'm multiplying by? Well, I suppose I could take 2 times -2.5. I know you're all thinking that, but I'll tell you what, -5 times -2.5 is not 10. So what I can tell you is this, and my last suggestion is look at this. Look for squares. I'll double underline that because that's what we're going to look at here. But I'm going to say and cubes. And what I mean by that is, I guess I know that these are not perfect squares, but think about what your perfect squares are. 1, 4, 9, 16, 25. Are you seeing anything related to these numbers here with those squares? Because if you're not, I'm going to throw this out there. What you're going to see is this. If I write these numbers down here, 1, 4, 9, and 16, you can see that all of these numbers here really are just 1 away from my squares. So as far as what I'm going to write up here goes, what I'm going to write is that as our rule, n squared is what we have, but I'm just going to say plus 1. We added 1 to all these values here, plus 1. So here's the thing. You notice that they alternated terms, and I shouldn't have blocked this off yet. We say 6, but alternating terms, alternating term signs suggests a factor of -1 to the n or -1 to the n plus 1. And so what I mean here is this. If you put -1 to the n and you multiply all this by -1 to the n, what we're going to do is we're going to make a little note here. This is a sign switcher. And what I mean by, hey, -1 to the n or -1 to the n plus 1, I guess what I mean is we should test this rule and see if we actually get these terms here. So I know I'll get our values here with this, but whether I get my sign or not is up to this. So we say C1. If we were to plug this in, I'll actually show my work on this one. We say -1 to the 1. So we would get here 1 plus 1, which is 2. Of course, we got our 2. But we'd say times -1 to the 1, which comes out to be -2, which is not the sign I need here. So here's the fabulous thing about this. If that doesn't work, if that rule doesn't work, what we're going to do is this. We're going to use n plus 1 as our rule instead. And I'll write that in purple here. N plus 1. Kind of sloppy. But we say n plus 1. And once you do that, what it's going to do, it's going to change this situation so that you put, like, say, a plus 1 there. Now all of a sudden -1 is to the 2. And now you've got a positive 2 as you need. So look for sign switching there.